Welcome in the new semester. Again, remotely, unfortunately. Hopefully, we'll be back at the university, but I'm not sure of this, to be honest. So anyway, we have to continue. We have to start the course. We will think during the semester how it's going, and is there any chance for any change of the form of the lecture itself. Anyway, we start remotely for sure next week as well, remotely. This time, because we are meeting for the fourth consecutive time during our course of studies, this semester we're going to have together a continuation of the introduction to microcontrollers course. This time embedded systems. So the course name embedded systems. What is an embedded system already today? If there is anybody not knowing me, then my name is Grzegorz Budzyn. I work here at the Faculty of Electronics and something. Then email you have from JSOS, and as well you can use the direct email grzegorz.budzyn@pwr.edu.pl. You can find me in room 244 in building C4 every Wednesday and every Thursday between 9 and 11. So in case of Wednesday, you let me know if you want to come, because I'll be at 9 for sure. Later, maybe. Of course, if other hours you would like to consult anything, then write me an email. You know the procedures, you know the communication channels. I think it's not going to be a problem. On Thursdays, I'm sitting here before the lecture because I have a lecture in the morning, early in the morning, and then this lecture particular. So in between, for sure, I'm in my room or somewhere around. So if you need some consultations, if you want to discuss anything, anywhere, then yeah, please come and visit me. In the new semester, one thing, as soon as I remember, because I will forget about it, small reminder, remember that next semester will be your last semester of the engineering course, which means that you must have a diploma next semester, and the process of choosing a diploma begins this semester. In fact, maybe not now, you've got the whole semester for the choice, but the process is that the best idea in case of your diploma's choice is that you first think about the subject you want to excel at, and then you discuss with some teacher. You find some teacher that's excelling at the subject that you want to excel as well. So it can be telecommunication, electronics, programming, the microcontrollers, analog, whatever you want. General from the whole robots, automation, whatever you want actually. Because you can choose anything. You can choose any subject during the as your diploma subject. Yeah. So then you just go to you find the teacher and you discuss with him or her the potential diploma subject, and then you agree. This is the best way. For the best way to have nice and working diploma thesis for the next semester. But you should start this semester again, maybe not in March, but you have the whole semester to search for some supervisor and for the subject. So don't wait for the supervisors to make their own subjects. Usually it's worse. So usually much better is to first find a supervisor and discuss with him her the subject, so that the subject fits you best. That's the subject fits you best. So that's a small remark for me, introductory remark, not really about the embedded systems, but about general 7th semester. seventh semester and your finishing of your studies. Okay, let's go. So about the program of embedded systems, what's gonna be analyzed here this semester. So what's my plan? Because the plan is evolving a bit, yet the basic rules are of course the same. So we finish the most important things about microcontrollers, about this path of your education that began with introduction, was continued previous semester with microcontrollers, and today we continue. We take over. So we finished last time on 32-bit Cortex microcontrollers. So we just started it, so it was just a very brief introduction into the world of our microcontrollers, and we take over from this point. So that's the major plan of embedded systems next week. So today something lighter. So I just want to start with the system embedded software architecture and with the benchmarking, so something lighter for the beginning, but then we continue next week. We start with and we analyze the existing Cortex microcontrollers, Cortex-M mainly, because this is our major interest area, together with some basic market view of very basic market view, because it's the market is really huge today about the ARM microcontrollers, but we have to analyze them. In the meantime, you will have laboratories. With the laboratories should have already started. I don't know exactly the term. Of course, now they are remotely, so it's just introduction. But in 2 weeks, you are definitely back at the university with physical laboratories in 142, where you will have a chance to program this time STM32, and this time in C. So no assembly programming, no assembly in the program, only 32-bit microcontrollers, STM32 407 discovery boards, giving you the chance to touch and debug the 32-bit microcontroller. So last semester was mainly about the 8 bits, and this semester only about 32 bits. So we don't go back to 8-bit world at all this semester. So it's not in the plan, and it wasn't planned. So what this course is about, of course, this is a continuation, and it's about this time the embedded systems based on some computational devices, but the computational devices, computational chips, or programmable maybe chips, are not only microcontrollers. Therefore, in case of embedded systems, we will have three parts that we will analyze. So we'll be analyzing embedded systems based on microcontrollers, and thus we will analyze the 32-bit microcontrollers and peripherals of those microcontrollers, so the most interesting ones from those advanced ones, of course, like for example DMA, that thus far we didn't have a chance to analyze, which is a very important peripheral, or a cache maybe, or some other security maybe, if we have enough time. We'll see. But then the second part is the DSP. DSP, because DSP as well can be an element of the microcontroller of the embedded system, especially the DSC. And we will not go into DSP world. You did have a DSP. You were to have DSP. By the way, because it's eligible course, did you choose it? Did you choose DSP?
Yes, we had it.
You had it previous semester. Okay. So your experience about the DSPs, so that's why we'll make it as short as possible, just to keep the course complete, let's say this way. So especially in case of DSCs, which are an improved version of microcontrollers, so slightly modified version of microcontrollers, straddling somewhere in between microcontrollers and DSP. So we will not go to DSP itself, but rather towards DSCs, and we'll touch this subject a bit. But then there is a third leg, and the third possibility, which is the FPGA and programmable logic. partly we did have it during the introduction to microcontrollers, but only partly, and we will repeat it with extending the subject. And you should have it already also this on during the laboratories. It is in the plan of for sure. We'll have 3 lectures more or less about the FPGA, about the features of the FPGA, how to use FPGA, what are the strong and weak parts of the programmable logic when using embedded systems. We'll see if we succeed in having a having a laboratory there with the FPGA. So it is in the plan. It will depend how well you will work on the normal programming, doing normal STM32 programming tasks. If everything goes well there, then also FPGAs will be there will be some exercises with programmable logic with VHDL. If not, it will be more theoretical, so just on the lecture. So we will see how it goes in case of laboratory. But there are those those 3 legs, the SPCU exercise, then previous semester, this semester microcontrollers and programmable logic. That's the plan in case of the embedded systems. The course consists of the lecture laboratory, as you know very well, and there is additionally a project. The project, so previously we succeeded, so many of you succeeded the project in making the project. Even some of you started this basic PCB boards and microcontrollers, which I'm pretty happy about. This semester the project is not with me, and but still you will need to design this time. The project is to be around 32-bit microcontrollers, so that you get even more experience. And yeah, so you are experienced after previous semester with the design of PCBs based on microcontrollers, this time 32-bit microcontrollers. So basically not much difference, but that's the plan for the project as well, to keep you excellent in designing devices based on 32 bits this time, on microcontrollers. Naturally, as it was before, so the rules of passing the course are same. So you must, first of all, you must pass all the forms, so the laboratory and the project and the lecture. And in case of lecture, we have two tests. As it was this time, it's not an exam finishing course, which means that the final test will be held before examination period. So in the last 15th meeting, in the last 15th week, the midterm test will be handled in week 8, and final for week 15, because we have to finish it before examination session. That's formal. The rules as well, like before. So if you pass the first term with grade very good and excellent, and you pass the laboratory and the project with grades very good and or excellent, then the second term will not be necessary for those of you. So these rules do not change. In case of your presence during the lecture as well, it's like it used to be, so it's not obligatory. So I will not be checking the presence. Of course, I'll be very happy to talk to somebody, so that you come and listen. But the presence is not obligatory. So that's how it is. What is the idea? What is the work plan for the semester? So today we start with basic introduction, so architecture of embedded system software. So this is our main point today, together with benchmarking. In fact, of course, the definition of embedded system, but this is just a terminology. Then we focus on the ARM microcontrollers. I don't know if 3 lectures, maybe 2 lectures. We will see. We will see how fast it will go. Usually it's something between 2 and 3 lectures about the analysis of the internal structure of ARM cores, and then about the analysis of the various cores, comparison of the cores. So we have plenty of interesting cores currently on the market. Among of them, not all real even available in hardware, and but awaiting for the hardware implementation. Still, we should analyze them because they most probably will appear on the market soon, sooner or later. Let's say this way, like Cortex M55 or 35P, because I'm mentioning I have this course in my mind. Anyway, plenty of things to be analyzed and to talk about. Plus the market view, plus the software. So the CMSIS itself, which is the software. It's a very strong point in using the ARM microcontrollers today. Something which you don't know, which is not known from STM 8s or from microchips or from Atmels. Here it's a huge thing, so that you can, for example, easily work with matrices, or you can build your own neural network without the need to use a Python or some Google toolkits for it. You can build your neural network just basing on the libraries delivered, on the low-level libraries. So this is a strong thing, and this is a very fantastic thing, in fact, simplifying the construction of the software and increasing the production pace or the development pace of ARM-based designs of ARM-based microcontrollers, embedded systems. So that's why a couple of lectures about it, and then the debugging, programming and debugging of the microcontrollers, the major features behind the debugging. So what needs to be present in a microcontroller or why the debug is running, maybe this way. So that's I want us to answer this question during this lecture. What's happening that we get the debug information out of the microcontroller, and how to make the debugging more efficient, or in other words, what tools to choose in a certain way of debugging. So that's about mostly debugging. Programming is not that. It's a side thing here. And then I want us to go back to the advanced peripherals, because we didn't finish, so we didn't touch the more complex ones, which are important today, like USB or Ethernet. So we didn't have a chance to touch them. I2S here is trivial thing, but during this lecture, I would like to talk about the wireless interfaces. So what options do we have in the wireless world? This becomes very important as today. First of all, it becomes important from two perspectives. This wireless interfaces. One perspective is that, of course, the users want to pay money for devices with wireless access, battery-operated devices. But about the battery and about the sleep modes, we talked during microcontrollers course. But the people really wanna get devices which are wirelessly connected. That's one perspective. Second perspective is that today on the market there are large groups of processors growing every day. In fact, maybe every week, but still growing at a fast pace. With radio block integrated, being radio block is being a peripheral in a microcontroller, which means that the use of such a microcontroller in a wireless world becomes trivial, because then it's enough to connect a few passive components plus an antenna, and it's there. So and then we have the microcontroller which is wireless ready. Wireless and with various interfaces, because we have the capabilities today. So we can find today in the market microcontrollers supporting the sub-gigahertz bands, where you can easily jump between the frequencies in sub-gigahertz, so mainly 315, 435, 33, 868, and 915 windows. With various modulations there, so in order to adapt to the channel and to be able to most efficiently use the channel according to the rules, because again the bands, sub-gigahertz bands, although they can be used for ISM use, so industrial, scientific, medical use. Yet they can't be used. There are also rules inside concerning the use of this modulations used in those bands. So, but anyway, we have microcontrollers with such modulations, and we have microcontrollers working with 2.4 gigahertz bands. So these are mainly the standards hidden here under the standards 802.15.1 and 15.4, because these are some of the standards used in the programming model of the wireless system. Still, this is the second perspective. So first of all, the customers want it. Second of all, we have the hardware, so it's very easy to combine it. So we have the hardware, so why not to get the hardware and sell it for more to a customers? And that's how the Internet of Things is happening, actually. So that's why during this part of the lecture, we'll focus very much on the wireless communications. This is really a strong thing, and I will show you how to use, so what are the capabilities that we have in using the wireless communication, based of course on the STM32 family, although on the market we've got many other manufacturers delivering interesting chips with Cortex-M0, Cortex-M3, Cortex-M4 core usually, plus the wireless block. Inside, wireless with virus modulations being supported in various standard communication standards being supported, so that there will be an introduction to this. So it's just about one, maybe two lectures spent on this subject, summarizing the features, summarizing the capabilities, but being experts from the microcontrollers field, you really must know, you really must be aware of the IoT modules, IoT capabilities, wireless communication capabilities that we have today in microcontrollers. That is single chip solution, single chip low power solutions, really available at hand, and very, very cheap, because the microcontrollers, the smallest one, they really cost below 10 euro. So low price as well. Then there is a time for the test, and then we go back to the more advanced issues. So I would like to analyze the functioning of the DMA, the functioning of pipeline, the functioning of cache here. That's what I want us to analyze, and then we move towards multi-core processing, so digital signal processing, and as well. Here I would like to analyze a bit, because the DSPs you did have already. That's why I would like to focus less on the DSPs as such, but to show you the new trend that we have currently, so that microcontrollers with two cores and the communication peripherals for combining those two cores, because the two cores means that they have to share something. They usually have some parts of the architecture which they share, some parts of the architecture which they have dedicated to themselves, the cores I mean, and there are certain blocks for sharing between those two. Then another element, which this is optional actually, the RTOS, and as well the question, have you had RTOS, or have you chosen the RTOS as a subject? Because you have such choice. Yes, you did choose it. You have it this semester?
Yes, we do.
Okay, so if you have it this semester, then I will replace this lecture with probably security microcontrollers, because of course there is no time if you have dedicated course that we repeat it here. So this lecture will be replaced by some security in microcontrollers, if we have enough time, because that these are the plans. It's a bit different with realization. If we have time, then security features of microcontrollers, very important thing today as well. very new, but very important, especially if we talk about Internet of Things. You know what's happening today in the world, and the cybersecurity in such an unstable world as we are living in today gets more and more important. And today, the microcontrollers, they are deployed in billions around us. They are deployed everywhere, and some of them have internet access, which means that they can be very easily accessed. And if they control even simple things like lightning or door access, then breaking in means a lot of troubles for the user. So cybersecurity is important, and today there is a lot of a lot of effort put to make the embedded system based on microcontrollers immune to cyber attacks, or as immune as possible to cyber attacks. So again, the things that's at least for me a bit queer, because if we have a microcontroller, then usually it's for driving an LED or some temperature sensor. So why to make it secure? But really today the microcontrollers are available in so many critical systems, and security breach here becomes an issue, and that's why there's a lot of protection, a lot of effort put in protecting the microcontrollers against unintentional usage. And if we have time during this lecture 11, then I have a lecture prepared about it, so we'll talk about it. Then lecture 12 to 14, that's about programmable logic. So major features make the construction of FPGA, the options, so not only FPGA, because also CPLDs, SSPs, SoCs. So there are a couple of programmable chips with, I would say, programmable hardware. Because in case of microcontrollers, the hardware is there and we are just writing a software. In case of this programmable logic, this is programmable. These are in general programmable hardware chips. Well, with some hardware describing language, we are modifying the internal connections, thus changing the functionality, thus obtaining new features. So about the classes of the chips, about the options we do have there, and about the hardware description languages that can be used for programming. So getting back, so extending what was already started during introduction to microcontrollers, extending and repeating some parts, so that you remind yourself how it is, and then you extend your capabilities. And again, I would like that you have it on the lab, but it will depend on your pace of programming, so how advanced you will be and how fast you will be working during laboratories. If you feel all the tasks that are about the microcontrollers, then maybe programmable logic as well on the lab. So I keep my fingers crossed about it. And then lecture 15, final test. So that's the program. In general, the program is subject to changes, is subject to modifications, like with this RTOS, for example, and as well, it will, we'll see how it goes during the semester about the pace of the lectures. If we don't lose any lectures on some occasions because of something, so hopefully, if everything goes smoothly, then hopefully we realize 100% of our program throughout the semester, so that you will have a chance to learn some. And I have a hope that you will find the lecture interesting and useful for your professional life. We'll see. Of course, the questions, of course, the comments, if you want, and of course, don't hesitate to stop me. So you know me. Maybe not very well, because throughout the previous 2 years we've been seeing each other mostly remotely. Yet, don't be afraid. You know, I try to be nice, so at least. So if you have any comments, questions during the lecture, so don't hesitate to stop me to ask the questions.
Excuse me,
Yes.
I would like to ask if the lectures will be stationary after 14th, or like always online?
I got stupid about it, to be honest. I was sure that in 2 weeks, so that last week, next week is our last virtual meeting. But as of yesterday's info from the dean, I'm not sure. I'm not 100% sure.
Okay.
I would like it. I would like it to be stationary, very much. But
okay. So for now, in terms of classes, there's an information that it will be probably online still.
I'm very much afraid of it. I'm very much afraid of it. For me, it's a very bad decision that I'm trying to fight with. But again, you have some other lectures today?
Mm-hmm.
Or
yes, we have all lectures today.
You have all
4
lectures
in a row.
yeah, so if you have all the lectures and the dean decides that they are to be remotely, then yeah, we can do nothing about it.
Yeah, for sure.
I don't know when they will this kind of thinking will change, because this is really a very bad decision, very bad decision. So, and what's the reason of having remote lectures if schools work normally and if nothing really happens at school? In schools, I really can't understand it. So I really can't hardly understand why we have those 2 weeks as remote learning, and continuing the hybrid learning throughout the semester. It's a horrible decision, but we can do nothing. So if you have 4 lectures in a row, then if they are to be remote, they will be remotely, all of them. We will see next week. Maybe something.
Yeah, okay. It's understandable, 100%.
Good. Okay. Any more questions? Yeah, the standard thing, the literatures. I didn't even put it here. Yeah, you know, the literature. It's nothing different as it used to be previous semester. So the major literature is not really the lecture. The lecture, what I'm saying, of course, this is the out of the lecture you can find the literature for the particular subjects, mainly as a data sheet or reference manuals or programming manuals or some technical articles on the web pages of mainly the manufacturers of the chip, like TI, like NXP, like Infineon, like Microchip. So there are a lot of information there. So if you want to extend the knowledge about particular things like the, for example, wireless interfaces or DMA or the programmable logic, so there are a lot of sources there. Still, the lecture is just the beginning. No books. So again, like previously, so I could put the literature here with the books, but the books, yeah, they don't keep the pace of the changes, and for me, it's a nonsense today to focus on books in the literature. The internet and mainly the manufacturers' websites, besides the lecture, are the main source of information here during this lecture. Of course, in order to pass the course, yeah, it's enough to know the material of the lecture. If you want to record me, feel free to do it. If so, I give a consent for recording. I have no problem with it. Yet I don't give a consent to spread the lectures on some portals, so you can use it privately for your own group use or the use within the group. No, that's it. So if there are no questions, then embedded systems, embedded software architecture, and benchmarking. So let's make a brief introductory lecture. Although let's have a few minutes break, maybe before this. So I don't know, 5 minutes. We'll finish earlier then as well. So let's have 5 minutes break just to breathe on, and then we'll get back to the lecture. Welcome back. So let's begin our lecture, our inaugural lecture this semester. And we begin with the definition what embedded system is. A simple, I think, straightforward. So embedded system is something which is embedded in something else. So in English, it's pretty simple. Embedded means that surrounded, or built in into something else. So this is a system designed to perform control specific function in a larger design, often with real-time computing constraints. Real-time means here predictable response, so that we know the response. We know when there will be a difference between the what will be the difference between the event happening and servicing of the event. So that's what is meant by predictable response here. So in case of embedded systems, there are plenty of examples of embedded systems, simple embedded systems. You can see here, simple robot with an embedded systems built in this robot. So the embedded system architecture, it's usually pretty simple. So you are designing it. Previous semester, during microcontrollers course, with the microcontroller as a central unit. Instead of microcontroller, we can have DSP, we can have programmable logic, but the microcontroller is the best here to be used because of the highest integration scale. So the microcontroller has so many peripherals present, then the integration of anything, of the sensors and of sensors, of some displays, of another modules is far simpler than with the use than when using DSP or FPGA. That's why the microcontrollers are preferable part of the embedded systems. And then we must have some programming, power supply, clocking, reset. So again, something that you to include in the projects previous semester and you had some experience with, and the output. So here is the motor control, but again, the output can be here the output is, for example, some servo of the ultrasound, whatever it is. It doesn't matter. It's not important at this moment. But that's it. That's the example of the embedded system. So it's not some miracle thing. It's the very standard element. So mainly, the embedded systems consist of some processing thing plus DSP or plus FPGA. It can be combinations. And today the embedded systems become complex. For different reasons, naturally. But the complexity sometimes requires either common use of a microcontroller and programmable logic, or common use of a microcontroller and DSP. And fortunately, and it became so important that today manufacturers are so the companies are offering us, as engineers, I mean, also combinations of those. So DSCs being a combination of a DSP inside and a microcontroller, or SoC, which are by SoC there is hidden the combination of the FPGA and microcontroller, or even microcontrollers, because sometimes on the market there are solutions with more than one microcontroller. Engulfed by the programmable logic plane. Of course, some electronics, in case of embedded systems, the electronics depends on what kind of system, what kind of device the embedded systems is built in. If this is such a simple thing as the robot, then here the system is mainly about the motor driving interface plus the power, of course, but it can be more complex. It can be much more complex device, and then some electronics becomes a lot of electronics. Still, the microcontrollers today offer so many devices inside, then the amount of electronics around the microcontrollers is really reduced to minimum. I remember times where the memory had to be outside the microcontroller, or the various logical buffers or some timers needed to be used outside the microcontrollers. Things non-existing today. So today we even have versions that microcontrollers have some basic glue logic, programmable logic planes, not planes, but blocks, even to get rid of the need for applications with single gates where necessary before, and today everything integrated into one microcontroller. That's why we love the microcontrollers, and we love using them in embedded systems as the heart of the embedded systems, because they give us the chance to build the smallest, the cheapest, the most versatile embedded systems out of these three possible solution. That's not possible in ESPs and in FPGA, so it's not comparable. Okay, then going back, I would say from a bit from the embedded system hardware, a few words about before we go further with the analysis of the hardware. Now, something aside, so some side subject, which is the architecture of the embedded software. So some of you, all of you, should have already had a chance to program microcontrollers. Some of you in a more profound, some of you in a simpler way. Still, you have some experience, so it's time to talk about maybe a bit the major capabilities that we have in designing the architecture of the embedded software. So that's not that obvious, and we have a few choices there. So what the choices do we have? So from practical point of view, when preparing a software for the microcontrollers used in embedded systems, because we take this path, we analyze this part. We can try to the software can be put in those categories. So that's according to my experience. So the round robin, state machines, round robin with interrupts, just interrupts option, function key scheduling. So a simple multitasking with the scheduler. Then the operating system with real-time version, and monolithic, so general purpose as well, because this is RTOS, and sometimes the monolithic is known under the name of GPOS, so general purpose operating system. So let's show what's the difference between those categories. So the first and simplest architecture that we can think of in case of microcontrollers is to use the control loop, so-called control loop, or so-called round robin, where there is a while function, and in the while function there are various functions. In the while loop, there are various tasks, I would say, being serviced, and the tasks are being serviced in a round robin fashion, because naturally we talk here about the situations where there are a couple of things that need to be done on the microcontroller, which is always the case. Actually, always. So only if you are making a program on PIC10 or ATtiny4, then you could make the program doing just one operation, and then you do it in assembly. But normally in microcontrollers, we always have to, for example, service the one sensor, another sensor, then do some calculations, then communicate with the world over some or more than one interface, the monitor something, power supply. So there are a couple of always there are many operations that need to be done. Some of them are time critical, others are not time critical, yet they have to be done. So they are a bit different requirements usually. Still, some so-called multitasking is required. Remember, we are talking about single core solutions right now, so we'll talk about the multi-core solutions during one of the lectures in the second part of the semester. Now, single core solutions, 8-bit, 16-bit, 32-bit, so it really doesn't matter. So we talk about C, about the level of C. So here in the round robin, the simplest, by far the simplest from the point of view of writing such a software is the version where there's one main loop, and tasks are called from this loop. The problem here, natural problem, is that it's simple. It's very simple. So we do nothing. We are independent on the hardware as well, because we are not using any neither timers nor nor interrupt here, so they are not required. So if you are afraid, so this is really the architecture of the beginners. If you do nothing, if you do not know nothing, then you start writing this in this way, in this method. Also, this is also a trap of people coming from the world of writing a software for the multitasking, fully multitasking systems, operating systems. So in other words, when you write a C program and you run it on a PC computer, then you can put a while loop, infinite while loop, and you can wait forever for something, for some event, for some value. You can calculate something forever. Nothing will happen, in fact. Because you will be assigned a slot of time, and by the operating system, by the scheduler inside the operating system, by the preemptive scheduler in the operating system, and it will just work. Yet it can't be easily copied. So this is the trap, as I mentioned, mainly of the beginners. This is mainly a trap because you can't really copy it to microcontrollers, because microcontrollers, there is of course normally in a bare metal version of the microcontrollers, there is absolutely no operating system, which means that there is nothing hidden underneath your program, and nothing will protect against the infinite loops. There as well. Therefore, in case of this round robin, it's going to work, but the execution time of this task, not the I, what I wanted to write. So the execution time of those methods must be finite, and must not be too long, and must not vary very much during the execution. Because if it varies, then such a microcontroller programmed in the round robin way loses its real-time capabilities. Because let's consider that the tau2, for example, or let it be tau3 in this example. The tau3 varies between 10 microseconds and 100 milliseconds, let's say. Let's consider that there is the reading of a temperature sensor task is not optimal, it's not well written, and from time to time it's either 10 or 100 milliseconds. What does it mean? It means that that the tasks that doing a time critical motor operation, because the motor operation is critical, usually in case of controlling it from a microcontroller, the operation of the motor, the loop that will this task will be called with the large time difference, or may be called with a large time difference, and it may call the malfunctioning of the motor itself, even the breaking of the motor. Why not? Sometimes it happens. So of course it depends on the motor, it depends on the application, but yeah, why not? I designed a couple of, I took part in the design of a couple of embedded systems that were capable of breaking themselves. So self-destruction feature, we can call it. So this is something that might happen. So that's the problem part. So the good thing is that it's simple, and period. That's the only good thing about the round robin and about the control loop, that it's simple. It's definitely not good in case of multitasking. Features, the tasks are dependent on each other. As you can see, another problem of this round robin is that we can simply add another task, so we can insert another task. It's simple, so we just add a call to a procedure, and that's it. Yet unfortunately, the total execution time of this loop is naturally the sum of the execution of the particular tasks, which means that adding a new task increases the execution time of the main loop. This situation, unfortunately, of course, may be a bit exaggerated, but to some extent it's very common. So that the task, this reading temperature sensor, why it may vary so much, because take into consideration the temperature sensor based on I2C interface or SPI interface, whatever. And such sensors need a starting signal, and when need starting signal, and then they need some time for measurement. And this short time, this 10 microseconds exemplary. Yes, some questions? May result from the software testing the sensor if the measurement is ready. Some line, for example, interrupt line or data ready line from the sensor. And this 100 millisecond may come from the time necessary for getting the data from the sensor, doing some calculations on this data. And actually this is very maybe exaggerated, a bit example, but just a bit exaggerated. It really is a problem because it really, in case of round robin version, the tau is not in the round robin version. The tau is not constant. The tau is not constant, and you can't rely on the execution time of the loop being constant. This is a feature of the round robin, the feature that really must not be forgotten. In case of round robin, one of the problems is that the tasks are equal, so it is possible here in the round robin version to try to make the priorities and try to run certain tasks. So this kind of prioritization alleviates a bit the problems with variable execution time, because then the tasks which are time critical, then they can be executed sooner than, or more often than the tasks which are non-critical. Yet it's just a plaster on still problematic method. So actually the round robin, it's simple. It's simple. It seems efficient, but that's in case of microcontrollers without an operating system. It's in my opinion very bad choice. So we can use it only for very trivial applications. The version of the round robin version, which is just tiny better, is the version of the state machine where we don't execute every task, but then depending on the state of our microcontroller, a certain set of tasks is being executed, is being run. Yeah, and again, this is something. This is the version, the state machine, which is not exactly much different from the round robin. It's even more complex because this time we've got various states which are non-existing in state machine. This version, from some perspective, is even worse than the state machine, than the round robin, because here the problem is blurred. I would say the problem with variable time execution timing, and the problem with keeping the time, the timing of the time execution. So it is even blurred because this time we've got various states, we've got various number of tasks being executed. Of course, the good thing about the state machine comparing with the round robin is that we don't execute unnecessary tasks anymore, because this time only set of tasks are executed in a certain machine state. So this is the good thing. This is the advantage of round robin, and some sort of improvement over round robin, over round robin of the state machine. Yet still you can't rely on timing of this method. Still everything is dependent. So if we modify the state machine over the next weeks, months, years after the software is finished, we have to retest everything, because the addition of this supplementary tasks, modifies all the timing dependencies, or may modify the timing dependencies and the behavior of our embedded system, of our microcontroller. So therefore, the state machine in a pure form, like it is shown here, purely software version, should be omitted. So like with the round robin, it's simple. Like with the round robin, it's non-hardware, it's hardware independent. So we are not using any timers or interrupts, all the resources of the microcontroller here, which is good, but that's the only advantage, like with the round robin, of this method. Then we come with something way more useful, with something which is in fact preferable in many situations in case of microcontrollers, and it's the standard, I would say, architecture today. So this is the round robin or state machine, whatever, but with the use of interrupts. So then we leave the simplicity. We'll leave the simplicity. So the idea is like this: so that we leave the simplicity of task switching, of cooperative task switching, or inside the main loop. So the simplicity of just placing the tasks that are to be executed, which are non-time critical, because that's the difference. So that non-critical tasks are being left in the main loop. Then they are executed with certain time difference, as discussed when the round robin was analyzed. But the time critical tasks, so the tasks which have to be executed at precise timing, or with precise delay from the external event happening, those tasks are then placed in interrupts. In interrupts, this type of architecture is very efficient. So this is really today the most efficient type of software. So when you want to write embedded program and embedded systems, or write a microcontroller, program a microcontroller, this is definitely something that you should be using, because this software is not very complex. It's not very complex, but it is definitely efficient, because we don't lose time. So whatever is necessary to be critical, to be executed in a certain time domain, in a certain time version, time dependence, it can be done because of the interrupts, and the other tasks which are non-time critical, they are just put into the main loop. Here the weak parts, because of course, as with everything, it has some dark sides, or darker sides than so some problems, but potential problems. So two main problems which I can see are: first problem with the round robin interrupts is that we have to use interrupts here, which means that we must be able to use interrupts, and this knowledge, especially for beginners, is not that simple. This is not so obvious, the interrupts themselves. And besides, we have to use the proper interrupts, because it's not about using any interrupt. We have to use the proper interrupt in an appropriate way. So that's not always so simple. So this is the first trap. Second trap is that the vectors, the interrupt service routines, so not the vectors themselves, of course, but the interrupt service routines, so these functions, button ISR and display ISRs, these are the so-called interrupt service routines. They should be inside them, there should be executed, or there should be placed only the code which must be executed in a timely manner, nothing else. So, for example, if we need to read some signal, measure some signal, let's consider that we want to sample some analog signal periodically with a period of I don't know, 10 microseconds. So in this interrupt, we should only sample the signal. We should only start sampling the signal. If we not sample, but we should only start sampling the signal periodically. And processing the signal should be designed to be done here in this part, in the round robin part or in the main loop part. So the interrupt should be kept as short as possible. Keeping them as short as possible is, of course, for the reason to be able to add another interrupt, to be able to add another events, servicing of another events in another interrupt, so that the interrupts do not intercept each other and they do not delay each other, because this may happen. This really may happen if the execution time of certain interrupt service routine is too long. So here is these two problems. So first of all, the problems with interrupt. Second, the problem configuration of the interrupts. Secondly, the problem with the length of the interrupt service routine, because it should be as short as possible. Anyway, in my opinion, this is for even medium projects, even medium-sized projects. This is preferable architecture. Round robin for very simple projects, round robin for interrupts. With small to medium-sized projects, large projects, function queue scheduler or operating systems, but about it in a moment. Architecture number 4, possible architecture number 4. So yeah, why not to use interrupts? Why not to use just interrupts? So the architecture where the main loop is empty and we put everything in the interrupts. Yeah, theoretically it is possible, especially when the interrupts can be nested, which is the case in, for example, in STM32, but in all Cortex microcontrollers, the interrupts can be nested, and we can set the nesting level as well in the NVIC. So we'll talk about it next week or in 2 weeks' time, how it works. So theoretically, it's possible. So this can be theoretically done, so that with the nesting. Without nesting, no, but with nesting, theoretically, this is useful architecture. Okay, this can be done, but from practical point of view, from my experience, historical experience, really 90% of the things, roughly, can be done here. A lot of code, maybe not for 90% of the execution time, but 90% of all the things that microcontroller is doing can be done in the main loop and are not time critical. Only a fraction is time critical, and for everything to work correctly, only this fraction should be put in the interrupts as privileged part of code. All the rest should be placed just in this part within the main loop. This gives really better. This gives really better results. Really much better results than version with round robin, than version with just interrupts, as you can see. Although this version is, I would say, so-so, still better than round robin or state machine. Yet, in my opinion, worse than just interrupts. That interrupts with the interrupts with the round robin with interrupt. Yeah, method number 5. Method especially useful in larger designs. This is the method that is called function queue scheduling. The method where especially useful when there's a group of people working on a software, a group of people, and in case of group of people, the best way is to isolate them from each other, so then they are capable of writing a dedicated piece of software, not really trying to find out or trace or avoid the dependence from other parts of the software, because then the less dependencies between the between the people, the more efficient and more easy it is to write a good software. So the function queue scheduling is the multitasking mechanism here, where each task here is a function, but actually it's a task queue scheduling, because we have the various tasks and there is a piece of privileged software which is switching the tasks. The task switching, so the function queue scheduling can be written in two modes. It can be written to support the cooperative multitasking, but it can be written as well to support, so the cooperative multitasking. You can see here some example I found, so that we prepared the pointer to functions, the table of pointers. So the func pointer is the pointer to the function. So we prepared the tasks table, then we prepared the function that's adding to the tasks table, another pointer to another function. Then we prepared the tasks and add the tasks to the tasks table. Some tasks doing something. And then we have the scheduler. So this is so-called cooperative scheduler, where the tasks are being switched, so being taken from this table, called from this table, and then switched between. So when one task is finished, then the second task is being taken by this scheduler. So if you think about it, then it's not really much. This kind of function queue scheduling is not much different from round robin, isn't it? Because we still have a list of tasks, the tasks which are just running by themselves, and when they finish, they just handle the control back to the main loop, this time to the scheduler. But this is the version of the function queue scheduling, so-called cooperative version. But much more efficient is the version of function queue scheduler with preemptive scheduler in a preemptive version. Preemptive means that the scheduler is not in the main loop, but it's rather in some privileged interrupt. Usually, so for example, in STM32 for this kind of operations, the SysTick is being used as the privileged timer. And in this privileged interrupt, the scheduler itself is just switching the context of the CPU, switching between the tasks, and then the tasks are granted time slots. The difference is that if here each task has to be written in a way that it handles back the control to the main loop. So no loops in the tasks may be, because they are forbidden to be used, especially no infinite loops. So infinite loops here are forbidden in this kind of function queue scheduling. And again, it's the same like with round robin. So this version of FQS is the same. But with the preemptive version, then it's completely different, because in the preemptive version, the switching of these tasks hidden in this table, in this task table, is done on a higher level. And during this task switching, there is replaced the stack pointer, the register content is replaced, and the program counter value is being replaced, and as a result, the tasks do not see each other, because the tasks live in their own time space. So it's from the tasks perspective, they are being executed completely in parallel. And in the version of FQS with preemptive multitasking, the tasks, you can write the tasks with a while loop, with infinite while loop, because you can wait forever for something in the tasks, like you're accustomed to do in a Windows-based systems, that you can wait forever, because in fact you are granted just one time slot for your tasks, okay, if you want to keep the microprocessor doing nothing during this time slot, it's your decision. It's the task's decision. So as you can see, two versions of FQS. This version, so with with cooperative multitasking, very simple, yet very much resembling the round robin with all the disadvantages of round robin. Version with the preemptive multitasking, much better, because the version with preemptive multitasking gives us the tasks which are which are not reliant on each other, and this is very good. This is very good. So then it gives us a lot of nice features. This preemptive version of FQS. Yet there is a dark side of the preemptive multitasking as well, bright side and dark side. The FQS with preemptive version of the FQS is not as efficient as the cooperative version of FQS. Why? Because here, like with the round robin, if task finishes, immediately a new task is being serviced, which means that the microcontroller is busy all the time doing something, but let's say it's useful. So of course the tasks are dependent on each other, so they have to be aware that they are all the potential users of the microprocessor. Yet this cooperation, if done well, delivers 100% of the performance, because the switching of the tasks is very efficient. In case of FQS, with preemptive version, in the preemptive version, the first disadvantage of this preemptive version of the FQS is that we lose time on switching context. Here, task number one finishes, so we just call another task. It takes nanoseconds. That's not a problem. In case of FQS, switching context of the microcontroller, a microprocessor in general, in fact, means that we have to change the stack pointer. So we have to take an old stack pointer. Usually we put it on a heap. We take from the heap the previous stack pointer, so the stack pointer of the tasks that will be running now. Then we have to as well heap the registers and take from heap the old registers, and as well the status register. If there are 16 registers plus status plus stack pointer plus program counter, of course, then it's about 20 reads and writes that need to be conducted on the heap and from the heap. So this takes microseconds comparing to nanoseconds here. But this is not the only problem. Another problem with the preemptive is that we can write a tasks that will do nothing, so that will just have a while one and waiting for pressing by a user a button that will be pressed once in a week. Yeah, why not? We can do it. The problem is that the microcontroller will simply do nothing during the time slot, which means that even if we have in another time slot a task that is extremely busy with calculating a complex IFFT or FIR filter or whatever is necessary, or calculating some processing some image data, it won't be granted more time, so it will also have one time slot. So CPU during slot 1 doing nothing, and during slot 2 doing busy all the time doing useful stuff, but slot 1 lost because occupied only once per week. So that's the problem of FQR with preemptive multitasking. That's why it's not that rosy, as you can see, and that's why the FQS with the cooperative version also is used sometimes, because it is more efficient. It's not requiring so much memory, because in the preemptive version we must have storage for every task with the structure with some structure of the data of the context of the microprocessor, because we need to be able to store the context and then restore the context back. So it's not all that rosy. Still FQS 2 versions, and then smoothly we can go further, because going from the FQS, the next step is the operating system, is the real-time operating system. The difference between the FQS and the operating system is that the operating systems deliver us some libraries, delivers us some data structures which are not available in the basic FQS, because FQS is just task switching mechanism. In case of operating systems, we've got the FQS implemented in some way, because there is the FQS of cooperative of preemptive version, but additionally to this FQS, we've got some additional libraries, we've got some additional data structures, we've got, for example, a support for the interrupts, for the events coming from the interrupts. So the RTOS is simply a bit extended version of the FQS, both preemptive or cooperative, because the operating systems can also be a bit different. Yeah, so generally we are generating a thread. So like previously, adding in the FQS, adding the tasks to the list of tasks, and then we start. So this is the version of operating systems with preemptive multitasking. Top FQS, preemptive FQS here is used. The good thing about the RTOS, so the bright side of the RTOS comparing to the FQS, is that the RTOS, we get the RTOS from the market. So especially if it is written free RTOS, like it is, but it's not the only free operating system, to be honest, on the market. So there are various operating systems there, and we have it already. So that's the good thing. The good thing is that we have a lot of additional tools available in the RTOS today, which are supporting, for example, the servicing of the interrupts, but as well we have tools for communication between threads, for sharing the memory, supporting sharing of the memory. For example, we've got lists, we've got queues supported, which are basically in FQS is not available. Here we have them, so we install such an operating system and it's there. But also we have certain goodies, I would say, certain drivers available. So like, for example, USB driver there is. Sometimes there are some calculation libraries available. Sometimes there is a support, for example, for FAT system in case of SD card memory, and some other things. It's not, so of course, it's far from complete. So there are only simple things added, simple things delivered with the operating system, with the RTOS. But thanks to this, the RTOS have RT. So thanks, so because there are not too many things, and because the libraries or the software added to the operating system is not too complex, then still the operating systems have real-time response, which means that if we implement such an RTOS on a microcontroller, then still the time between the event and the servicing of the event will be constant, pretty constant, and pretty short. So it won't go into seconds, but rather will be between micro and milliseconds, in micro to millisecond time frame. What's the bad thing about the RTOS is that it's heavier than FQS or than previous architectures. It's heavier. That's one problem. Second problem about the RTOS is that we lose a bit of control on the hardware. So it's all right if you want to just write the application software on top of it. But to be honest, if we use microcontrollers, even 32-bit microcontrollers, we really like, or we need to have an access. So if we build an embedded systems based on such microcontroller, quite often we need to control what's happening with the pins, with the peripherals inside. With the RTOS, that's the nasty stuff about the RTOS itself, then we lose a bit. So it's covered by the operating system, it's covered by the libraries and drivers that are there, but they are not efficient usually. And of course, it is RTOS. Of course, it will work in many projects, in many situations, but the problem is that we lose a bit of a control. Of course, it's not as bad as with the monolithic or general purpose operating systems, where we lose complete control over what's happening. But fortunately, the GPOSes we can't usually implement on microcontrollers, because the microcontrollers are missing in general. They are missing virtual memory system. And monolithic operating systems, in order to fully function, you need virtual memory system, and this usually is missing in microcontrollers. At least today it's missing. So maybe in the future it will be added, but at least today it's missing. So usually, from our perspective, we are not able to use on microcontrollers monolithic operating systems. So general purpose, of course, we are losing support for graphics, support for extended music coding, and whatever it is for gaming. But that's not something we need from in microcontrollers applications today. So these are the major options that we have. So monolithic operating system is not an option, but all the other options are on the table, and you can use them. You can sometimes, it's even that in some applications, for example, RTOS is better. In another applications, the round robin with interrupt is better, and in another application, just interrupt would do best. So it really depends sometimes on the applications. All options are on the table, with some pluses and minuses that I try to show you during this lecture. So, any questions? If no, thank you very much for today, and see you next week, unfortunately remotely.
Thank you.
See you.
Bye.
Thank you. Bye bye. Have a nice day.
Can I ask you something?
Yes.
Okay. Can I share a screen?
In a moment. Yes, you can.
Okay. I have a question about not about lecture, but about VHDL. So here I created finite state machine. And it's working, so that's good. But how it works, because what I wanted to do is to fetch data from the one memory, and I found out that I need to wait one clock cycle before I get the data. So I created a special state which works like this: that I load the address.
Then you switch to wait state.
Yeah, load where to state what I want to go next, and go to the wait state. And this works, as I said, but before I did it, like I had separate wait states for every wait. The synthesizer was detecting the finite state machine, and now it doesn't. So my question is, is this approach correct?
It's a multi-source. Yeah, you have a problem. So multi-source means that you are assigning to the same. You know, in case of FPGA, the problem is that you are not allowed to assign to the same signal, port, or variable in different processes.
Yeah, it was unrelated issue. It's working now.
Okay.
So maybe I'll show you what I meant. If I remove this wait state, and don't worry about the finite state machine. Will be still there. Okay, like so. And now without this wait state. It's analyzing finance machine for best encoding,
Mhm.
and it's optimizing it. But if I have this wait state with variable, it doesn't do it. So yeah, again, question is, should I worry about it or not?
You should test it. Of course, because now, okay, the problem is that now it detects, the software detects that there is a state machine, and that's why it detects the states and shows you the encoding. With this next state, probably there is some logic problem. Yet, what you do with next state? So where you assign it? Here. Okay, no, it shouldn't be a problem. So it's just that it's not detecting properly that it's the wait state, but it should work, because what you are doing is that you temporarily assign the next state to the state variable, and then you are the next state to the next state variable, and only then you assign it to the state. No, it should be no problem. It's just that it's not detecting this as a state machine, but it should make the proper state machine. It should make the proper state machine. So that's not a problem.
Okay, thank you.
Okay, thank you,
Sorry,
Van.
Mr. Buzin, can
Yes.
you hear me?
Yeah.
I'm a double diploma student, and I wrote you an email like 2 days ago. I passed already this course during my semester studying here, and I was wondering, like, is it possible? Because like Mr. Palushinsky called you like in the beginning of the previous semester, and asked if it's possible to transfer the credits from this subject for my study here now.
Mhm.
And I want to know, like, is everything okay? Do I need like to do something, because there is a bit of changing? I saw that there's like 7 ECTS and you are not holding labs anymore.
Mhm. If you pass the course, then yeah, you don't need to pass it again.
Okay, so
If you pass it once, then you have it passed.
okay, and you are grading us at the end of the semester.
Yeah.
Okay,
But if you need the grade earlier, because right now I can't give you a grade in the system. I will be able to give you the grades only at the end of the semester, because then the system will allow me to do this. To be honest, but then yeah, just remind yourself about the grade so that you pass the course once, and yeah.
But in this schedule, we have also like project, but I didn't have it. Like, is it okay just to give me grades for the previous one, like for the labs and for the lecture, like for 5 ECTS? Is it okay?
Wait a moment. I don't know if you're enrolled in the same course, to be honest, because this course, the name is the same, because you mentioned about the embedded systems, which are for the embedded robotics Master of Science course, which is 2 hours of lecture and 2 hours of laboratory. This course is pretty similar, to be honest, but it is for engineering course, for advanced applied electronics, for electronics and computer engineering. Sorry, it's for engineering course, and it does have a project, so this is different course. And the project is different from the lab, because the project itself is about making a PCB project with microcontroller on board. So this is different, and this is something which is missing in the comparing to the embedded systems on the robotics. So this is not completely the same. This is not completely the same, and the project is not by me, but by Oleg Gulshek, I think it is. So slightly different.
Can you please again like repeat the difference between this embedded system